Hello and welcome to part 2 of chapter 6 in our video series. So here's where we ended in chapter 6. We had just drawn the long bone, and this is a very important concept in anatomy. So really understanding the gross anatomy of a long bone, being able to draw it, define all the different parts and pieces like the diaphysis, the epiphysis, the articular cartilage, the cavity, all of that. So make sure you are comfortable with your drawing of the long bone. So we're going to jump into the second part of chapter 6, and we're going to go from kind of this bigger tissue, and we're going to get a little bit smaller and a little bit more microscopic. So we're going to keep going. We're going to look a little bit more at the cells of the bone tissue, kind of what really makes it up. So we can see we have our bone cells here, and your prefixes and suffixes are really going to help you out this time. So you can see that we have some of the best ones to know for this tissue. So osteo, of course, means bone. We're going to say that the word part blast is going to be to build. Site, of course, always means cell. And clast, we're going to use a C word to kind of keep it together. We're going to mean this to crush. Okay, so we have a C here and a C here, a B here and a B here. So we can keep our blast and our class apart from each other. Osteoprogenitor cells are actually the cells, the stem cells or the germline cells that create a lot of the cells that you see here, like osteoblasts, osteocytes. And you're going to actually find these cells in linings like the endosteum, which lines the inside of your long bones in the medullary cavity, or the periosteum. Remember, the word peri means to surround, and this actually lines the outside of bones. Here we can see the different cell types in action. So let's look at the osteoclast first. So this guy is huge, absolutely huge. So we've got all these nuclei that you can see here. This one has like 4 or 5 nuclei. And then it has this very unique blob-like shape with all of these tentacles, which they call the ruffled border. And it's going to create this big cavity because what it's doing in here is it is eating away and breaking up the bone. And you know, at first you're like, oh my gosh, why would we have any type of cell that would destroy our tissue? And its main purpose is to make sure that it's going to release calcium into the bloodstream. We have to have a consistent stream of calcium available in the body. So osteoclasts have a very important job. Now, when you're young, once the osteoclasts have finished and they've kind of eaten away some of your bone, you see over here our osteoblasts will come along, and if there's enough calcium in the bloodstream, a little bit of excess, they will take that and they will start to build back up that area of that bone. And so we have this nice balance when we're younger between osteoclasts and osteoblasts, which is great. Now what happens, especially in women, is over time, unfortunately, the osteoclasts really start to ramp up and our osteoblasts start to go down in activity, and we start to see this big imbalance. And of course, this will lead to diseases like osteoporosis or brittle bones as we get older. We also see our osteocyte. They are really, really important in maintaining and keeping your bone alive. So we have this really nice slide here of bone tissue. And the really big takeaway here is, let's just look at the size of the cells. Look at the size of this osteoclast. It is gigantic and it is eating away. You can see all of the clear here, and it is eating away that bone. We have our little osteoblasts over to the side here, and of course, if you look close enough in our osteocytes, we have the house. You can see that white area there. That is the lacunae, and we've talked about the lacunae a couple of times regarding cartilage, and you're going to see it in bone as well. The little house to hold those cells that are trapped. So as far as compact versus spongy bone, Compact bone is going to be nice and solid and strong, smooth, and very dense in its makeup. You're going to find it on external surfaces of long and flat bones. Spongy bone, on the other hand, is built to have a very open network, lots of airspace. So we say that we have these really narrow spicules of bone or narrow barbs of bone or anything like that. And that gets really hard to describe. So they actually have a word for all these little narrow parts of bone. And this is the word we're going to start using. It is trabeculae. So when we're talking about spongy bone, the little parts of bone that you see going in all different directions are called trabeculae. We're going to find spongy bone at the ends of your bones and the internal surfaces of bones. It's really going to make the bone more flexible and light. This is going to be our next drawing. The compact bone setup. It is the compact bone setup that helps deliver all of the nutrients, and it makes your bone one of the most active tissues in the body. And it also makes it one of the easiest tissues to heal because it has this amazing setup. Super, super cool. So we're going to take the time to draw out what compact bone looks like under the microscope. And we're going to kind of define all of the terms that you see here. So I've got another blank slide coming up. And I always kind of use the analogy that it's like a city. So each little part of compact bone reminds me of an individual city. So we're going to have this nice central part. We're going to make this more like the downtown. And we're going to have, this is going to be our downtown area. And we're going to have streets that actually radiate around the downtown. So it's a very interesting city in that everything is kind of in a circle. So you can see all of these streets circling the downtown. By the time you're done drawing the basic shape, it looks like a target or a bullseye, kind of. And so we've got our downtown in the center here. And then we have all, I drew 1, 2, 3 circular streets. So then we have to have houses in our town. So I'm going to draw some houses on these streets. So just draw some houses on these streets. You just randomly place them. And you have to have residents in your town. And we know that if you have a house, you're going to have a poor little trapped cell. That's going to be our resident that is trapped in this house, living on this circular street. Then we're looking at this and it's like, okay, so we have our downtown, we have everything happening in the downtown. How do we actually get supplies and nutrients to all of your citizens trapped in their homes? And so you actually have a canal system. Think of Venice. Think of all these, beautiful, really cool cities that have canals going through them and riding on gondolas and things like that. And so your osteon city, your bone city, is set up that way to where you have all of these tiny canals radiating, connecting the little circle streets that I've drawn and going to all the houses and supplying the houses and keeping the residents alive. And so that's kind of the basic setup structure of an osteon. And of course, so that's one osteon. So this whole thing right here, let's draw a bracket here. This whole thing I just drew is the osteon. Now you'll also seen see it as Haversian canal or Haversian system. Same thing. They just like to use different names. So we have our osteon. And of course, the bone has tons of these osteons. So we can draw one over here. We've got our central canal. Let's draw some nice circular streets around that central area. Let's throw some lacunae, or those cavities, those houses that you see. We've got to have residents. So put some cells trapped in their poor house. And we have to be able to supply those houses. So draw yourself some canals, like beautiful canals on Venice, whatever you want to think of. So we've got this nice little canal system. And so we've got several of those. And we even have some circular or kind of half circle streets that will connect different osteons. So we've got some different streets running between, but they don't make like a full osteon. So we have all the rest of these that we need to talk about and label in our little drawing. So first, let's start with the central canal. Well, that's pretty easy. It's right smack dab in the center. I'm going to draw it on this side. So we have our central canal, and it's going to have all your arteries, veins, supplies, etc. It's going to help nourish the osteon. So you know what, we can even draw some arteries, some veins inside here to bring some of that blood supply to this osteon. Next, we have the streets, those circular streets. So the circular streets are called lamellae. Think of it like you live on Lamellae Street. And they go in a concentric ring around the central canal. So the ones that we've drawn are actually called, so I'm just going to pick this one right here. This is a concentric lamellae. Oh, I better make sure I spell that right. And these are rings around the central canal. In this drawing, I even gave you an example of another type of lamellae, and that is the interstitial. Inter means in between. So we see these guys here. They're in between these osteons. This is this one right here, interstitial. Oops. And they're in between osteons. Oops, I guess I should put lamellae. They're in between osteons. The one that I can't show you because this diagram is not big enough are circumferential. So you'll just have to use your book to get the definition for that one. Next, osteocytes, of course, are the cells that live inside. So there's an osteocyte. And they are the cells that maintain bone. Then we have your supply system. And those are the little canals. So these are the canaliculi. I really like that name. It even has the word canal in it. So there's the word canal, canaliculi. These are the tiny canals that connect everything. I'm just going to put that connect, because I'm going to run out of space. Oops. Oh, come on. That connect. It's not really wanting to write. It's supposed to be neat. Jeez. That connect. So they're going to make sure you get all the nutrients you need out to all of your residents that are living in this osteon. An osteon is one of the units, and I like to use the city analogy. It's, a city. We have our central canal as the downtown. We have the lamellae as the streets. Oh, and I forgot, it's not on this list, but you got to know what you live in. You got to know what your house is called. And that's called the lacunae. That's the cavity. That's where your osteocyte lives. So I'm surprised it's not. I didn't put it on our list there, but that's what you see that your osteocyte lives in. So that's one of our other big drawings for Chapter 6. Here is what it looks like under the microscope. We have a nice ring. It almost looks like a tree stump or something, that you can see all the tree rings or tree growth. So that's one osteon. You see the nice central canal. You see the lacunae, and you see all the radiating, very skinny little canals, the canaliculi. Let's look at spongy bone. The microscopic anatomy of the spongy bone does not look like that. It does not have osteons, but you can see the trabeculae. So you can see those little spicules of bone. So we've got one here. Here's a really nice one, an up close one here, this dark pink. And we can see those little random pieces of bone that are throughout the spongy bone tissue. And so we can see those trabeculae. So where does bone come from? Bone forms from a process called ossification, actually hardening of a tissue. And there are two different ways. There's intramembranous. So intra means inside, membrane. So it develops from a certain type of tissue that you see in an embryo. And there's not many bones that are created this way. Basically, the flat bones of your skull, a little bit of your facial bones like your mandible, and a little bit of your clavicle. All the rest of your bones come from something called endochondral ossification, which means we have inside cartilage. Chondro means cartilage, so inside cartilage. And this is how most of your bones are created. And we can see the steps here. We have this nice cartilage model when we are babies. The cartilage starts to calcify. And we usually see it start, you can see in the shaft here, or the diaphysis. Then it keeps forming, we get more and more nourishment, and we start to see other centers of ossification, which means hardening areas. And so we started in the diaphysis, then we start to see hardening areas at the ends of the bones. And this process just keeps happening and happening until the bone matures and we see the structures that we see in an adult, which means we see more of our spongy bone on the ends. If it's a long bone, we see a medullary cavity if it's a long bone. And then we see all the compact bone on the outside. As far as bone growth and getting taller, there's a couple of different ways. Interstitial growth is when you want the bone to grow in length. So that inter means inside. So this is when we're going to use the epiphyseal plate. And it's just a layer of cartilage, and you're usually going to find it at the boundary of the epiphysis, the end, and the diaphysis, the shaft. And it's really hard to kind of see here, but you can see all these gaps in this child's hand. And you can really see that a lot of the bones aren't even really developed here in the wrist. Look at this one. This one's forming right here. And so you can actually see the forming of the bones, and the bones are going to kind of grow into these spaces. And that's the epiphyseal plate that you're looking at. So interstitial growth is really going to happen along the bone's length, making them longer, but we can also make the bone wider. And so that's what you see in this bottom example here. This is called appositional growth. This goes along the same way when we talked about the growth of cartilage and we talked about the interstitial and appositional. So this is going to help on the outer edge of the bone and really give the bone more diameter. And this appositional growth is going to happen in the periosteum. Bone homeostasis is another thing your book talks about. They don't get into like a lot of depth. That's more for physiology, but you do need to know that this is an active tissue. There's lots of growth and maintenance and repair happening at all times in your body. Most of it depends on the hormones and your diet and your exercise. Bones really respond to gravity and pulling of muscles. So, we really actually learn this from astronauts, believe it or not, and what happens to their skeletons in space. So we need to move our bodies, and we also need to make sure our hormones are regulated. And that's another reason why females see a lot of bone density changes more than males, because estrogen can really affect the bone homeostasis and can affect the level at which osteoclasts work. Bone fractures, there's lots and lots of different fractures. I would just look at the tables. Some of the more famous ones that people see when they think of a really bad break, this is the one they think of, comminuted. This is when your bone just shatters and you have more than two pieces. Another one that they have on here is mostly seen in children. That's the green stick fracture. So this is more in children because their bones are still pretty bendable, and so they don't break all the way. And they just kind of bend. Or you might get maybe a little bit of a partial break. A lot of people will get things called incomplete or hairline fractures or something like that in their bones. The one that we see a lot in athletes is this one right here, the spiral fracture, where their foot stayed on the ground and then they got twisted and maybe got hit as they were twisted, and you can see that force and that break twist right up their bone and with the fracture. We do see a lot of stress fractures in athletes as well, usually from running and really just overdoing stressful impact. So you can see all of them in one table here. And probably the most famous fracture happened in 2013 during a game in March Madness. And my students talked about this forever. And it's pretty graphic. If you want to watch it, I have the link there. But this required some extensive repair to get him back to good, because that was a very, very intense break, an intense fracture. Ouch. But even though it was an intense fracture, his body will heal that. And if you follow your doctor's orders, it'll heal so well, it will be hard to see even on a radiograph. Now, unfortunately, that poor guy needed a rod, and so you may see some remnants of the rod and screws that were in the bone and things like that. But fracture repair happens in 4 steps. And the very first thing that happens is you bleed. Well, that makes sense because there's so many blood vessels running through each of your osteons. And so we don't just say, oh, you're going to bleed. We make it sound a little more medical, and we say you're going to form a hematoma. and basically are going to bleed into the space because you've broken all of those blood vessels. Okay, that makes sense. Your body kind of cleans that up, and it's going to form a quick Band-Aid here. So your body's just going to throw some really weak material together, try to slap it together just to hold the ends and allow your blood vessels to start to regenerate and get back together. So it's a very soft, very weak callus. So we call it a fibrocartilage callus because it's made of fibers and cartilage. It's pretty weak. Then you get a better bandage, and we get a bony callus. This is mostly spongy bone, as you can see there. You can see all the air sacs there. So still not great. And then a few weeks later, we have the spongy bone replaced with some compact bone, and we really start to remodel the bone in step 4 and make it look just like it did before the break. So we have hematoma formation, fibrocartilage, callus formation, bony callus formation, and bone remodeling to get you back to good if you break a bone. Bone markings is what I think one of the harder things to learn about the bones, and so chapter 6 just kind of introduces them. And there's a really, really great table, and I have it down below as well, table 6.17 in your book. And it's a really good introduction. And it just kind of helps you look at the definitions before we get into the next chapter. Chapter 7 has a few, but chapter 8 really gets into specific bone markings. So I really like this table, and it really just breaks them into some nice categories and saying, okay, what am I going to see at touching surfaces? Remember, that's what articulating means. So when bones touch, what is it going to look like? Is there going to be a large smooth area? Is there going to be like a really small flat area where the bones touch? Is there going to be something kind of round and prominent? Or something really smooth or grooved? So what am I going to see where the bones touch? What about depressions in the bone? Is there going to be like a deep depression? Maybe kind of just like a flattened out or shallow depression? Maybe just a narrow groove. So are there any depressions in the bone? There are a lot. So look at this category. There's a lot of things that stick out of the bone. We call those projections. This is usually where muscles and things attach. We can have really narrow projections. We can have really big projections. We can have any process, that any bony prominence called a process. We can have these really weird extensions of bone called rami or ramus. We can have spines. So there's lots of different types of projections. We know we have lots of openings in bones. We have to be able to get nerves and blood vessels through the bone to other tissues. So you're going to see canals and fissures. You're going to see a lot of foramen. Meatus is kind of a famous one because that's used for your ear canal, kind of digging through some of your bone to create your ear canal, and some of your sinuses. So I really like this good general table. You can really get a good handle on just some general terms. When you're in chapter 8, will help when you learn the more specific. Like, hey, on the radius, you're going to see the deltoid tuberosity. Oh, well, I know what a tuberosity is already. Now I know that there's a special one for the radius. And so here you have some really nice pictures, a little bit more up close on what they look like. And we'll play around with these a little bit more in chapter 8. We talked a little bit more as we went through the cells about the aging of the skeletal system, but you are going to lose your ability to produce good collagen, so it's not going to come together as well. you are going to lose your ability to absorb calcium and other minerals, and you're going to see that decrease in bone mass because of osteoclasts and things like that. And so this could lead to osteoporosis or more brittle bones. So that really wraps up chapter 6. And we always try to end by looking at our objectives and going back through. So the second part really focused in on objectives 7 through 11. Looking at the microscopic anatomy of compact bone, that's really where we did our drawing. And then looking at spongy bone. Spongy bone just has trabeculae. There's really no osteons or anything else special about it. Number 8 was describe and compare intramembranous and interchondral ossification. One happens in a membrane, one happens in cartilage. Number 9, explain the components of bone that enable it to grow and be remodeled. So looking at that epiphyseal plate, and then that helped it grow. What about remodeling? Well, that goes to the cells and the setup of bone itself. Number 10, describe the steps involved in healing a fracture. There are 4 steps. And number 11, identify the anatomic terms that describe the surface features of bone. This one is going to take you a while to really study. So my note card people, make some note cards with, the name, the definition, and a drawing of what it looks like. Because I know from experience that your anatomical features of bones or those bone markings are the toughest part of the skeletal part of the test. So that is it for part 2 of